My name's Malkolm Hinnemo from Uppsala University in Sweden. What I want to present is surface-enhanced Raman scattering of graphene, and we have compared this with and without residues. So we start with CVD graphene, where we have added gold nanoparticles. So we evaporate the gold nanoparticles, and they will spontaneously form evaporate gold film, and they will spontaneously form gold nanoparticles. And then we have characterized this for different nominal thicknesses of gold. And if we look here on the enhancement, we can see that at 8 nanometer of gold, we get very large enhancement, which then goes down a little bit as we go to 12. This effect can be understood from the SEM pictures seen here. At 8 nanometers, we have particles, long particles, but they are not connected. While at 12, we start to get more of a connected film. This means that at 8 nanometers we have more of polarization, and this will increase the surface-enhanced Raman scattering. So what we have wanted to do then was to compare this for with and without residues. So we have graphene, everything is CVD graphene, but some of it has some PMMA residues, the normal ones left from transfer, and some of it is very, very clean. We have a new method that will make sure that we have unmeasurable levels of PMMA. So what we have compared then is seen here is first with and without bulk nanoparticles, just try with and without the residues, and it's somewhat lower on our residue graphene than it is on the clean. But the interesting part is what happens when we have gold nanoparticles. The enhancement is much larger on the clean graphene than it is on the gold nanoparticle ones. So we wanted to try to understand why. So we've done simulations of gold nanoparticles on the graphene with a varying thickness layer of PMMA. And the results are seen here, where we have the clean graphene. We can see two peaks, but that is mainly because of a highly simplistic model. And then as we add PMMA and of increasing thickness, the distance between the particles and the graphene goes up, and so the enhancement goes down. And we have a fitting here. We try for the different thicknesses our enhancement at 633 nanometers, and then we've seen a fitted, and around here, around 0.6 nanometers of PMMA, we have about the same enhancement as we have in our results. So what we do here is that we're trying to assume how much, approximate how much PMMA we have, and that would be something a little bit lower than 1 nanometer, and one layer of PMMA lying down on the graphene would be approximately 0.6, 0.7 nanometers thick. So we think that's around the level we have. We also have compared with literature of what people have seen before of this enhancements on surface enhancements of graphene. And what we can see is that on metallically clean graphene, they see enhancements of around 100 times, 120 times is the maximum reported. On CVD graphene, it's been lower, much lower, 20, 30, up to 50 times. And what we can see here is that our PMMA residue graphene is on this 20 times enhancement, while our clean graphene is at 120 times. So we believe that the discrepancy between these results are simply due to residues from the transfer. Thank you.